Another of our objectives for this section is to explain the gas laws, relate them now to what's described as the kinetic molecular theory. Sounds highfalutin and fancy, but it's it's our basis of our understanding of how gases behave. All right, so what in the world do we mean by the kinetic molecular theory of gases? You might remember that the kinetic energy is energy of motion, so it has something to do with that sorts of idea. So there is a number of concepts involved here. The first one is this. The gas consists of tiny particles, either atoms or molecules, moving about at random, nothing more orderly. The second principle is that the volume of the particles themselves is negligible, very small, compared with the total volume of the gas. In other words, most of the volume of a gas is empty space. That makes sense, we would think, I hope. Number three, the gas particles act independently of one another. There are no attractive or repulsive forces between particles. This is an important assumption for the kinetic molecular theory of gases and how gas laws work. And number four, collisions of the gas particles either with other particles or with the walls of a container are elastic as long as you have a constant temperature. Elastic means they don't lose energy when they have collisions. And the last one, and this is a key thought, is the average kinetic energy of the gas particles is proportional to the Kelvin temperature of the sample. So this, as you can already probably imagine, is why we're constantly careful to use Kelvin temperatures when we're doing calculations with gas laws. So these are the five principles in this theory. How do they apply to the ideal of the various gas laws? All right, so if we look at a gas in a box at the top there, and we're going to do things to it. So for example, what if we, as A shows over here, decrease the volume, you squish it down, and we're talking about what happens to the pressure when the volume changes. So decreasing the volume of the gas at constant number of moles and temperature, we haven't changed those, but you're squishing the box to a smaller volume, increases the frequency of the collisions with the container and the walls, and that increases pressure. So collisions with the containers and walls, in fact, relates to pressure. So the smaller the box, the more often the collisions occur, and therefore the pressure increases. The second change represented here is to increase the temperature. If you increase the temperature, and that means the kinetic energy is related to the temperature, right? At a constant number of moles, we haven't let any gas molecules in or out, and the pressure is therefore subsequently going to increase because the energy of the particles is greater with the temperature increase, and that will verifiably increase the volume of a gas. Just like when you heat up a hot air balloon, the gas gets bigger. So that fits here with the kinetic molecular theory. The third one, then, is what if we changed the number of moles? So if you take that box at the top, if you counted all the little dots in there that represent gas particles, you can tell that the box below probably has some more. And so if you increase the amount of gas in the box, in the gas sample, as long as the temperature the temperature is constant, the pressure is going to increase because we have more particles colliding with one another, and therefore the volume of the volume of the gas. So the pressure increases. Wait a minute, I said that wrong. So as long as we have constant temperature and pressure, the volume of the gas is going to increase. Constant temperature and pressure, hello. Because the volume is increasing because you've got more moles of gas in there. Correct. Then the last one, and this has to do with Dalton's law, the law of partial pressures. Changing the identity of some of the gas molecules has no effect on anything else happening in the gas. So if you put in some different molecules, little blue spheres instead of little red ones, the pressure and volume and temperature are not affected by having different gases in there. In other words, the total pressure is still related to the total number of moles, and it doesn't matter what the identity of these are. So this all fits with our kinetic molecular theory because they have no interaction with each other. It doesn't matter which gas molecules are in the sample. Let's see how else we can apply these concepts. So the kinetic molecular theory tells us that the gases, the speed of the particles is related to the kinetic energy, which is related to the temperature. And there's another aspect to this that's very informative for our further conversations with later topics. The average speeds of various gas molecules at kind of ordinary temperature, like 25, speeds are given meters per second. That's fine, you don't care, it's just a unit. And looking at these different samples, it's conspicuous that hydrogen has a much faster speed than carbon dioxide. Well, what's the deal? The higher the molar mass, the lower the average speed. So little particles move much faster than bigger particles. And so there's a relationship here that is conspicuous to know. So keep track of this idea that the greater the molar mass, the slower the particles move. We will use this in some other places as we move along. And another way of relating this thought is to look at these two graphs. On the left, we have the distributions of speeds for one gas, namely nitrogen gas molecules at 3 different temperatures. So this average speed is related to the temperature, but as this graph on the left shows you, the average speed is lower at 100 Kelvin than it is with the average speed at 700 Kelvin is much higher. So it's somewhere up here versus somewhere down lower. So the average speed is related to the Kelvin temperature, regardless of what gas it is, and this is just an example with nitrogen. Of course, the speed of the gas is related to its mass, but this is different temperatures for nitrogen. Then again, we're going to look at the distribution of speeds for different gases at the same temperature, which is related to the graph on the previous slide. If you look at chlorine and nitrogen and helium, the one with the highest mass has the lowest average molecular speed. The one with the lowest mass is going to have the highest average molecular speed. In this particular example is shown to be at 300 Kelvin. It doesn't matter. It's just a set of data that makes this comparison to relate molar masses to average speeds. Another graph that shows the same kind of idea is informative and interesting a little bit. If you're looking at helium, for example, in this particular graph, the distribution of speeds is shown at 200, 600, and 1,000 Kelvin. And what percent of helium has what speed? Well, notice that for any one temperature, there is a distribution of speeds. It's not just one number. There's some lower than higher, but you're looking at an average speed when we describe these things at a given temperature. So the average speed of helium at 200 Kelvin is somewhere in this range of, well, I don't know, something greater than 1,000. And the average speed at 600 Kelvin is somewhere else here nearer 2,000. And the average speed at 1,000 Kelvin is, well, I don't know, maybe something like that. Somewhere in the range, somewhere near 3,000 perhaps. And so the distributions of speeds are going to flatten out in the maximum, and the maximum moves higher as the temperature increases. Remembering that they're not all just one speed. It's kind of a distribution of speeds, but there's averages that we will tend to talk about. So this all relates to the kinetic molecular theory and how those things are described in terms of average speeds of gases, etc. I hope you find this helpful as you work on your assignments in learning these concepts. Ask more questions. See you in class.